Good afternoon. Welcome to the beginning of our unit on modern physics. It's a very short unit. It goes by very, very fast, but there's some really interesting questions that get raised in the modern physics unit, and this is where the majority of the research in physics is done today. Now, by modern physics, our definition of modern is not quite the same definition of modern physics. Modern physics basically encapsulates everything from about 1900 onwards, okay? Before 1900, we had discovered basically most of the rules that govern mechanics, which is the first half to two-thirds of what you've studied this year, and we had a pretty good idea of how electricity worked. There were some things that we didn't quite know, but we had a pretty good idea of how a lot of that stuff worked. And the reason that we started to study, and we already knew waves were pretty set for us, with the exception of light waves. We had a pretty good idea, of most of those things, but everything that came afterwards, everything that you're going to learn about now, they're newer discoveries, later than 1900. And the reason we started to make this jump right around this time is because our technological levels really increased. We were able to use and harness electricity to run these more and more complex machines and tools and experiments, and that's where we start to get all of these neat results. Let's start back at the beginning of modern physics. And in order to talk about this, we had to go through our waves unit first, because you had to get a good basic foundation with waves in order to understand what's coming next. We've spent the first about two-thirds of the year talking about particles, and then we spent about a month or so talking about waves. And we know from that waves have some strange properties that regular particles just don't have, such as constructive and destructive interference. Now, I'm just going to sketch those out for you. We know that if you have two wave pulses that look like this, and they're traveling towards one another on, let's say, a string or something like that, when they overlap, they don't just pass through each other. They're not like particles where they just bounce off each other. Instead, what will happen to these waves is they will grow, and when they're overlapped, their displacement, the shape of the wave, will be reminiscent of the shape of both of these, but we're just going to add the amplitudes together. So you get something like this in the middle. Okay, we just add the amplitudes together. That's constructive interference. Destructive interference would be something like this. Let's say we have a couple of square pulses heading towards each other. When they overlap, they're going to cancel each other out. Particles don't do that. When particles hit each other, they don't grow to be 2 times as big. They don't cancel each other out. They just bounce off each other and go back their way. Also, when waves after waves are done overlapping, they just continue going the direction they were going as if nothing had ever happened. The other thing that particles don't do is diffract. So what I'm going to draw is a barrier, and this barrier has an opening in it, and we're going to draw some wave fronts coming towards the barrier. Okay. Remember, wave fronts they show that all the they show points on a wave that are all in phase with each other. Now, the barrier is obviously going to reflect some of this wave, but some of it's going to get through. Once it gets through, something kind of strange happens. The wave starts to spread out beyond the barrier. This is known as diffraction. Particles don't do this. Particles, if you had, let's say, a tennis ball or something going through this barrier, it would just continue to go straight. It wouldn't start randomly curving to the left or curving to the right. It would just go straight. Waves, on the other hand, because of Huygens' principle that every point on a wave acts as a point source for the rest of the wave, because you're taking away some of those points that we're setting up these nice plane waves, you're now going to have the wave start to spread out and kind of curve and diffract around that opening in the barrier. These two properties are important. They were featured in a really critical experiment from the 1800s that is known as the double slit experiment. And a good picture of the double slit experiment is shown below. You have a light source right here. Okay, this is actually a light bulb. I know it's getting a little faded here. We have a barrier with 2 slits in it. And then you have a screen back here that light can show up on. So the whole point is light is going to pass from the light source to the screen, but it's going to have to pass through one of these 2 slits. Okay? Now, as light passes through these slits, if light was a particle, there was this big debate, okay, stemming from the 1700s onwards. Everything else we've been able to classify up to this point as either a wave or a particle. But what's light? Light is kind of weird. We're not sure whether it's a wave or a particle. This experiment aimed to answer that. If light was made of particles, like imagine particles passing through these barriers. Like imagine, so I play tennis. You can get these things called like tennis. They're basically tennis ball machine guns. You can think of them like that. They'll shoot a ball at you, and your job is to hit it back, and then they'll shoot another ball at you and another. Imagine you have like a tennis ball machine gun here, and it's set up so that it fires towards this barrier with the two slits in it, and then there's a screen in the back, and the screen has like Velcro on it. So if the tennis balls hit the barrier, they'll just bounce back. If they go through one of the slits, then they will go and stick to the screen. The Velcro will catch it and they'll stick to the screen. If this was tennis balls, you would expect there to be just like two spots, or two basically patterns on the screen that are filled with tennis balls, right behind this slit and right behind this slit. The tennis balls don't randomly veer off to the left and the right. That would look weird. Well, it was theorized if light was a particle and you put this barrier there, then you should only get two bright spots behind the barrier. Look what we got instead. We got 1, 2, 3, 4, 5, 6 when there's only two holes. That's really weird. Particles don't do that. However, we do know that waves, when they go past a barrier, diffract around that barrier. They diffract through that opening. They start to bend and curve. And we know that light, or waves, when they meet each other, they can interfere constructively and get bigger than they normally would be, or they can get smaller and totally cancel each other out. So this pattern is describing what's actually happening here. This pattern, this interference and diffraction, describes this. The light actually spreads out as it goes through this barrier, and then there's some places where the light undergoes constructive interference. There's some places where the light undergoes destructive interference. That's why you see bright and dark fringes, bright spots and dark spots. So this seemed to settle that light was actually a wave. This showed that light had wave-like properties because after passing through this barrier, we saw the light diffract, spread out around the barrier, or after it goes through the barrier, and also interfere to produce these bright and dark spots. So scientists reasoned that if light were made of particles, it could never do this. It would only show up as just two bright fringes. Since it didn't do that, light must be a wave. I'm going to show you this real quick. This is a basic example of the double slit experiment. I don't know why that's so bright. There we go. All right, so I have a light source here that's going to send out plane waves of light. You can see them. Now, the plane waves are coming to this screen with two openings in it, or this barrier with two openings, and then they're going to end up showing up on this screen here. We even have a little graph to show us the light intensity at different points. So watch what happens when the first waves get through, okay? They are very clearly diffracting around. We still see that we have brighter fringes and dark fringes to show the wave nature of light, the crests and troughs. But watch what happens once those two, once the light that has diffracted through the barrier starts to interfere with each other. So now we're going to get some interference. You can see the interference pattern developing. And now take a look at this screen. Okay, this is a real life example, and I can show you this in class. I will show you this in class, that this is a real thing that happens. Look how many bright fringes there are on the pattern. I count, I think, 9 of them. There's only 2 openings. But because of how the interference pattern works, and because the light is diffracting through those barriers, we get more than 2 bright fringes. We get many, okay? We get 9, and we even get some dark fringes. If there was no such thing as diffraction, you would expect there to just be kind of like maybe like more light here, and then it kind of gradually fades out. But there's some spots where there's no light at all because the light is getting canceled out because of destructive interference. This is just a simulation of Young's, Young knows the guy who did this. This is just a simulation of the double slit experiment, and it shows good proof that light is a wave. It has wave-like properties. If light was made of particles, you would only see bright spots here and here, and that's not what you see. Light must be a wave. Or so we thought. There's another phenomenon in the 1900s, okay? Young's, the double slit experiment was, I think, in like the mid-1800s. The next experiment that we're going to talk about, known as the photoelectric effect, happened later. This happened in the early 1900s. So, The photoelectric effect basically stems from this. Scientists had discovered, I don't want to say discovered, but scientists had basically figured out how to generate currents by this point. They had figured that sort of stuff out. They had figured out enough about electricity where there was someone with a bright idea that said, okay, we know that light is a wave, and we know that for waves, the energy of the wave is proportional to the amplitude of the wave. And for light, amplitude basically relates to brightness. So someone thought that, hey, if we increase the brightness of the wave, that's increasing the amplitude, that should also increase the energy. Let's take a bright light and shine it on a piece of metal. What we're trying to do here is we're trying to create a current. Remember, metals, they hold on to their electrons very loosely. And we had discovered by this point that if we give enough energy to an electron, we can ionize it. We can take that electron away from its parent atom. We can cause the parent atom to become charged because it was originally neutral. It loses an electron, it loses a negative charge. It now has a positive charge. So we've ionized it. That extra electron, therefore, it's just out there. And if we do that enough times, we can create a current. We can create a flow of electrons. So scientists theorized one way that we could create a current should be to shine a bright light on a piece of metal. Electrons should ionize and then create a current. If we have a brighter light, since brighter light means bigger amplitude, which means bigger energy, or so they thought, that should increase the current. Not only should it make there be more electrons, it should also make the electrons more energetic. We're giving more energy to them, so they move faster, and we should be able to record this. So I'm going to show you now the photoelectric effect. Here's the setup of the experiment. We have a light that can shine on a piece of metal. There's a battery down here to induce a voltage if we need it. And basically the idea was, as we turn up the intensity, we should get bigger and bigger currents and faster electrons. So I'm going to do that. I'm going to turn up the intensity. Right now the light is infrared light. So 5%, okay, no current yet. Okay, nothing yet. And, we got all the way up to an intensity of 100%, a very, very bright infrared light, but I don't see any sort of current being generated. Interesting. Well, let's try, I suppose, okay, maybe not infrared, let's try red light. Okay, here's some nice red light. Let's shine that on the metal. Okay, I don't see any current forming, Let's try a different wavelength. Let's try, I don't know, like yellow maybe. Still nothing. I'm at yellow at 100% intensity, and there's no current flowing. This is really weird. Scientists thought that just increasing the intensity would create a current. Well, let's keep going. There's some wavelengths we haven't tried yet. Let's try green. Okay. So we see that we're starting to get some electrons, okay? For some reason, it took a little while to get the intensity up there. Let's bring this back down. Okay, so it's a lower intensity. We're still getting electrons at green, with a green light. We're just not getting very many of them. As we turn up the intensity, watch what happens to the electrons. Does it make them any more energetic? No, it doesn't seem like it to me. It just means that there's more of them. Okay, so for some reason, anywhere like yellow, orange, red, infrared light, that does not seem to be providing a current. Let's keep decreasing the wavelength. Notice that the wavelength started off with infrared. It's a lot higher, so we're decreasing the wavelength. Let's go down to blue. So now you notice not only are we getting some more electrons, they're also moving, some of them are actually moving faster. That's kind of interesting. We're actually recording a current now. Let's go to purple. Now we're getting even more, and there's some that are moving even faster. And I think the simulation is kind of bogging down, which is unfortunate. But even if we go all the way to UV, look at that. Now we're getting a ton of electrons. Okay? There's some still that are moving kind of slow, but most of these are moving very, very fast, and this is the biggest current that we've had. So something about our understanding is not quite right here. scientists thought that by simply turning up the intensity, we would get more energetic electrons and more of them. They were kind of right. If I turn down the intensity here, that makes it so that there's fewer electrons, but they're still moving with lots and lots of energy. So it seems that the intensity can make there be more flow, but it doesn't make them any faster. And the intensity does nothing if I don't have the right color, if I don't have the right type of light, if I don't have the right wavelength. Okay? Because if I try this with orange light, I'm not getting any sort of current. There's some minimum, like right about at green somewhere, where they start to flow. So something weird is going on, something unexpected is happening here with the photoelectric effect. It's not just intensity, it's also the frequency. Both of those matter. Here's how we ended up explaining the photoelectric effect. All right. So, turning up the brightness did not necessarily make electrons start moving. In fact, the current only flowed if the light had a large enough frequency. So we saw that we were turning down the wavelength as we went from red to orange to yellow to green to blue to ultraviolet. The wavelength was decreasing. That means the frequency was increasing. So there was a minimum frequency that had to be reached before a current was created, before these electrons would be ionized. Brightness could increase the current once it started, but it couldn't create a current all by itself. And it didn't make the electrons any more energetic. It didn't give them any extra kinetic energy. It did not make them move faster. So this idea, or this experiment showed that light can't be a wave. Showed that light can't be a wave because the energy was not proportional to brightness. And remember, brightness is the amplitude of what we would call of light. Amplitude of light basically shows us brightness. So the idea was every other wave that we've ever studied has this property where its amplitude is proportional to its energy. For a light wave, or what we thought was a light wave, the amplitude was the brightness, but brightness didn't give any extra energy to the electrons. So light can't possibly be just a wave because of this. The other experiment proved that light can't be just a particle. Now we just proved light can't be just a wave. In addition, it also can't be a wave because you would think if light is a wave, then it can just keep supplying energy to an electron, then it will ultimately free. It doesn't matter how long we put the light of, let's say, of a red wavelength on the metal, we were never going to get any sort of current out of it. Okay, so something else is going on here. The normal theory of light as a wave did not work. Instead, it now seemed as if light was composed of particles that had a certain amount of energy contained within them. The model for that is in this picture right above. If you have a wave of a certain wavelength, of a large wavelength, it doesn't contain. You can think of that piece of light as this, this particle of light, whatever that means. It doesn't have a big enough, or it doesn't have a small enough wavelength, whatever that means. Therefore, it does not release any electrons. A smaller wavelength, for some reason, can seem to contain more energy. That could release an electron. An even smaller wavelength contained even more energy, and that could release an electron faster. That's what we seem to be finding here, that light was acting as a particle, and if this particle had a small enough wavelength, that's the only time we could get electrons to flow. By the way, photoelectric effect, this is one of the reasons that Albert Einstein is famous. He worked on this. Here's what we ended up going with, okay? Einstein and some other people, notably Max Planck, who I'll talk about in just a second, developed this theory called quantum theory. It wasn't just those two, it was many, many people over a number of years. Here are the main tenets of the theory. Electromagnetic energy is emitted or absorbed in discrete amounts. Discrete amounts, so think about like electrons, okay? We spent a lot of time talking at the beginning of the electricity unit that you can't have half an electron. You can't have a third of an electron. You either have a whole electron or you have nothing. You either have, it's got to be a whole number. So electromagnetic energy is emitted or absorbed in discrete amounts, and those amounts are called quanta, Q-U-A-N-T-A. The singular is quantum. Okay, so basically what we're saying here is it builds on the idea that you can't have half an electron, and you can't have, like, there's got to be a certain smallest amount of electric charge. This is the same idea. There is a smallest amount of energy. It's discrete amounts, and those energy packets, if you will, or particles, are called quanta, or singular would be quantum, one quantum of energy. Each little quantum's energy is proportional to the frequency of the radiation. Anytime you see the word quanta or quantum, you can think, as if it refers to light, you can think of it as like a light particle. There's an actual name for it, which we'll talk about in just a second. Okay? Each quantum's energy is proportional to the frequency of the radiation. And the equation for determining the frequency was discovered, and it is in your reference tables in the modern physics section. This is below waves. I'll get to what a photon is in just a second, but this is the equation. The energy of a quantum, a particle of light, is equal to h times f. E stands for energy, h stands for Planck's constant. Planck was one of the scientists who worked on this, and f is the frequency. So we have E equals hf. However, we know that since v equals f lambda, and this is light, light travels at the speed of light. That's c. That's the symbol speed of light in a vacuum. So if I didn't know the frequency, I could say that the frequency was equal to c over lambda. So there's actually another equation for the energy. If you don't know the frequency, you can figure out the energy of the light particle by doing h, Planck's constant, times c over the wavelength, where h is known as Planck's constant. And Planck's constant is on the front of the reference tables. Symbol is h, and has a value of 6.63 times 10 to the negative 34th joule seconds. Joules times seconds. Okay, so speed of light is on the reference tables. We now have this new constant h, Planck's constant, which allows us to determine the energy of a particle of light given either the frequency or the wavelength. And I keep saying particle of light, particle of light. Okay, we're talking about electromagnetic energy. Basically, light is emitted or absorbed in discrete amounts, little, almost like packets of energy. What we really call those most of the time is a photon, a light particle. That's what photon means. Photons are weird, okay? We can consider light as being made up of individual photons. Each individual photon has some energy, and it also has some momentum. But here's the weird thing, okay? You know the equation for energy, for let's say the energy of a particle is, well, first of all, a particle would have kinetic energy, which means the energy would be given by 1/2 mv squared. Likewise, momentum of a particle is given by m times v. Photons are massless. They have no mass, yet they can carry energy and momentum. That's super weird, okay? We know of nothing else that works like this, and yet this is the truth. This is how they actually work. Photons can even transfer energy and momentum to other particles that have mass, and these interactions follow all the normal conservation laws. So photons, these light particles, can interact with things like electrons. They can interact with atoms. And they can give those atoms either momentum or energy or both. And the conservation laws that we've talked about, conservation of energy, conservation of momentum, they still apply even though the photon doesn't have any mass. If this sounds weird to you, like what are you talking about? You have the right idea. This is crazy, crazy stuff. Okay? We just spent about 50 years thinking that light is simply a wave, and now we get this other side of the coin where we can imagine that light also works somewhat like a particle. So quick recap. Double slit experiment showed that light has wave-like properties. It interferes and diffracts. The photoelectric effect showed that light has particle-like properties. It can have energy. It can have momentum. It can transfer these to other massive particles, yet it doesn't have any mass itself. Light has some particle-like properties. It has properties of both that appear in different situations. Light is this third category of stuff, okay? It's neither a wave, it's not a wave, it's not a particle, it's this third category. It's in a category all by itself. This idea that light has both properties of waves and particles but isn't really either one is known as wave-particle duality. You might think that that's the end of the weirdness, but it actually gets one step weirder. Later on, like in the past 50, 60 years, scientists did more experiments. Someone got the bright idea, okay, we know that light, if we go back to this experiment, the double slit experiment, we know that light will interfere and diffract with itself, and we'll get those weird patterns. What if we did that with electrons? I mean, electrons are particles. We know electrons are particles. We know that if we take electrons and we fire them through these slits, then we're going to get an interference pattern. Or excuse me, that we won't get an interference pattern. We know that we're just going to get two little areas of electrons, right? I mean, that's got to be what happens. Electrons are particles. That makes total sense. So someone did this experiment. They took electrons and basically they shot them through a barrier with two slits in it, and they wanted to see what pattern it made on the screen behind. Well, wouldn't you know it, the electrons interfered with each other. They made a pattern like this. Okay? Imagine tennis balls doing this. It wouldn't make any sense to you. Okay? How did the tennis balls end up over here if there's only two slits? So someone had the idea the electrons must have been hitting into each other. They must have been kind of knocking each other out. Okay? Pushing them to different spots. It was just luck. So someone came up with a way to fire one electron at a time. One electron can't hit itself out of the way. You'd need multiple electrons to do that. Guess what happened? Even when we shot one electron per second at this barrier, and it had to go through one of these, over time, we got the exact same pattern. Even with one electron getting shot over time, or one electron shot at once, we still got an interference pattern. The electron was somehow interfering with itself. What's the takeaway here? If electrons are interfering with themselves, electrons that we thought of as particles, they also have wave-like properties. And we redid this experiment. We did it with electrons. We did it with protons. We did it with atoms and molecules. We even did it with something as large as a virus, which is, I don't know the exact size of a virus, but at the very least, hundreds of thousands of atoms. And guess what? All of these things that you would think of as a particle exhibited wave-like properties. They interfered and diffracted. That's insane. All of these things sometimes act like waves. The conclusion is that even though we think of things as this is either a particle or it's a wave, the conclusion is that everything we think of has some wave-like properties, and it has some particle-like properties. This is weird. Okay? If we were able to run the experiment, we were able to do enough of these, and it would be very tough to tell, but this golf ball looks like a particle to you, right? It actually has some wave-like properties. Everything in existence has the properties of both a particle and a wave. It exhibits this duality. Light is the weirdest, okay? Light easily has properties of both waves and particles. But it turns out that everything in existence has the properties of both particles and waves. That's enough for wave-particle duality. I'll be back in the next video to talk about the model of the atom and atomic spectra.